This is the tutorial for the Finding the Center of the Milky Way Lab. This lab recreates one of the most important experiments in early 20th century astronomy, the work that allowed astronomers to figure out where the center of our galaxy is located. To do this, we'll use the Vizier Astronomical Catalog service to get the most up-to-date information about globular clusters, the largest star clusters in our galaxy. In the early 20th century, astronomers understood that we lived in a vast, flattened collection of stars we call the Milky Way galaxy. However, they couldn't really estimate its size or even what part of the galaxy our solar system is located in. The reason this was so difficult is because the plane of our galaxy is a very dusty place, so it's hard to see through it. What astronomers really needed was some way to see outside of the plane. Fortunately, two important observations came together at that time to make it possible to get a better sense of the size and shape of our galaxy. The first of these was that globular clusters, vast collections of up to 1 million stars, seemed to be surrounding our galaxy outside of the plane, and they were concentrated in one direction. This suggested that the center of the galaxy would be in that direction. The other was that we could measure the distances to these clusters using certain types of variable stars called Cepheid and RR Lyrae stars. We'll look more closely at how we use variable stars in the lecture portion of the course. But in this lab, we'll focus on the distribution of globular clusters in the Milky Way and use that to find out where the center of our galaxy is located. An astronomical catalog isn't a place where you can buy stars and planets. Instead, it's a list of related astronomical objects with important data listed on them. So there are catalogs of stars, or galaxies, or star clusters, etc. The Vizier Astronomical Catalog service is an online clearinghouse for these catalogs. We'll be using the Vizier site to get an online catalog of globular clusters in the Milky Way galaxy. There are 147 galactic globular clusters in this catalog. When you follow the link in the lab to the globular cluster catalog, you'll see a series of checkboxes that let you select what information you want to see on these clusters. While you're welcome to pick as many of these as you like, you should definitely pick the 4 listed in the lab: the identification, the galactic longitude, the galactic latitude, and radial distance from the Sun. Note that the galactic longitude and latitude are similar to longitude and latitude on the Earth, but they're defined by the plane of the Milky Way galaxy instead. Also make sure you change the number of objects on the left side of the screen to 200 so that you get the entire catalog instead of just the first 50 clusters in the list. When you're ready, hit the Submit button to get your complete list of all the known globular clusters in our galaxy. Calculating and plotting information for 147 clusters is a fairly boring project. It involves just repeating the same work over and over again. Fortunately, we don't need to use all 147 clusters to have a good idea how these objects are distributed around us. If we take a well-chosen list of 30 instead, it should give us the same information. So we need a way to pick clusters from this list. The order of the clusters in the list isn't random. They start at right ascension equal to 0, and then move systematically around to larger RA values. So you don't want to just pick the first 30 clusters on the list. These will all be concentrated in one direction in space, and will give you a biased result. Instead, you should select a method that picks clusters from throughout the list. The lab write-up suggests a few possibilities you could use. Since 30 clusters is roughly 1/5 of the total list, you could just pick every 5th cluster on the list. This could start with any one of the first 5 objects and then add 5 to that till you get to a total of 30 clusters. Another option is to use a random number generator, such as the ones in many spreadsheet programs, to pick clusters from the list. A third possibility that combines the other two is to break the list up into groups of 5 clusters and then use a random number generator to select a cluster from each group. Whichever method you choose, make sure you describe how you made your choice in the lab write-up. Once you have your list of 30 clusters, fill in the information on them in the first 4 columns of Table 1. Before we can plot the data, we need to make a couple of adjustments to the distance information. The first step is to change the units in the distance. At the moment, they're listed in kiloparsecs, that is, thousands of parsecs. We'd like to turn that into kilolight years, or thousands of light years instead. A parsec is 3.26 light years, so we just need to multiply the distance in parsecs by 3.26 to turn it into light years. The second step is to convert to the projected distance. These globular clusters are mostly outside of the plane of the Milky Way. So when we measure their distance, we're measuring how far away they are both along the plane and above or below it. Since what we're interested in is how far along the plane of the galaxy these clusters are, we need to convert the distances into distances projected onto the plane of the galaxy. The way you do this is to multiply the distance by the cosine of the galactic latitude. You can find the cosine function on any scientific calculator. Make sure it's working in the correct units by first calculating the cosine of 90. If you get 0, then you know it's working in degrees. If you get a different number, then you'll need to determine how to change the angle units your calculator is using into degrees. So, for each galaxy, calculate the cosine of the galactic latitude, and then multiply that number by the distance in kilolight years. To see an example of this, let's look at a cluster that has a distance of 9 kiloparsecs and a galactic latitude of 30 degrees. We first convert the distance from kiloparsecs to kilolight years. This gives us 29 kilolight years. This goes into the 5th column in Table 1. Then we find the projected distance by multiplying by the cosine of 30 degrees. This gives us 25 kilolight years distance. This goes into the last column in Table 1. You just follow these steps for all 30 galaxies. Most people have some experience working with, or at least reading, the sort of square Cartesian graphs we see most often. Polar graphs work a little bit differently. Instead of plotting along horizontal and vertical axes, you'll be plotting locations on a circular graph instead. The two numbers you need for this are the radius from the center and the angle around the circle. For the radius, we're going to use the projected distance from Table 1. Look at the polar graph attached to the lab. Moving out from the center, make each circle represent 10 kilolight years. So that the first one is 10 kilolight years, the second is 20 kilolight years, etc. Make sure you label these on the graph. For the angle, we're going to use the galactic longitude. This runs from 0 to 360 degrees, with the angles already marked on the polar graph. Let's look at an example of how we plot points on here. A cluster that is 25 kilolight years away and has a galactic longitude of 75 degrees would be halfway between the second and third circles and halfway between the 60 and 90 degree lines on the graph. Since the distance is the distance from our solar system, that means we are located at the center of the graph. So the center of the galaxy will not be in the center of the graph. Instead, it will be in the center of the main concentration of globular clusters. Once you've plotted all of your clusters, determine where the center of the globular cluster distribution is on the graph, and record this in Table 2. Don't forget the units. Congratulations, you've found the center of the galaxy. The second half of this lab is an exploration experiment. This part is as much or more work as the part we've done, so give it the time it needs. The goal here is for you to apply the techniques you've developed in this lab to a question you can explore yourself. You're welcome to come up with your own exploration experiment, but if you do, you should probably check it with your instructor to make sure it's doable with the tools you've got. If you don't have your own suggestion, we've listed a few here. One possibility would be for you to return to the Vizier Globular Cluster Catalog and use one or more of the other checkboxes to select other information about these clusters to examine. The catalog includes data on things like color, absolute magnitude, size, and velocity of these clusters. If you have an idea on how some of these things might be related to each other, you're welcome to test it with these data. You could also try investigating one of the other catalogs in the Vizier database. Data on almost any kind of astronomical object can be found here. You may want to work with your instructor to help you navigate the range of possibilities, but this list lets you find collections of data on almost any kind of astronomical object outside of our own solar system, so there's an amazing range of questions you can tackle here. A third option is to figure out which constellation has the most globular clusters. The best approach in this case will be to plot the RA and DEC positions of the globular clusters on a chart showing the boundaries of the constellations. Whether you pick one of the options we suggest or come up with one of your own, you'll need to do a write-up that includes your question and a hypothesis that states what you expect and why. Then you'll need to describe all the steps you take. This should be the sort of detailed, step-by-step description that would allow someone else to duplicate your work. Your write-up should also include all of the data you take, including any graphs or histograms you create to test your hypothesis. Finally, include your conclusions, where you discuss whether your data supported your hypothesis or not, and what went right and wrong in your exploration experiment.